And time for our last speaker of the day.
Are you guys ready for a filibuster? All right. Thank you. Hey, everyone. My name is Jesse Heim. Thanks for being here at this 5 o'clock. Today I'm going to talk... Oh, there's a screen. I'm going to tell you about a project we were calling TheFARRM, Forced-photometry on all Roman-Rubin matches. And not only is TheFARRM a great acronym, Stanford is also known as TheFARRM, hence the name of the project. And this has been in great collaboration with folks at KaiPak, myself, Ani Chithi, and the wonderful people listed here. So if you haven't heard, Rubin LSST just began last week. So we have begun the 10-year journey to collect 20,000 square degrees of photons down to RF 27.5. Very impressive. And of course, by design, a lot of the Roman core community surveys will land on a Rubin pixel as well. So that's the green area. The green box sort of shows you where the southern accessible sky is from Rubin, and then the major surveys from Roman, also in colors. So for this talk, I'm going to talk about, I'm going to focus on HLWS for now, because it is by far the largest, about 5,000 square degrees at the end of 5 years. Hence, we'll have the most amount of overlap with Rubin. All right, so upon the dawn of these two great missions, I think it lies for us to reflect on what the best way to maximize the science synergies to come from these missions are. So one of the more obvious ways to do this is to combine the deep multiband optical colors from Rubin with the very sharp imaging from Roman, right? Not to say there's not other synergies like time domain stuff, but I think this is the bread and butter sort of science synergy we can really go for. And the question is, how do we actually optimally do that? Now, some of you may think, you load up TopCat, you load an LSST, good luck. You load up Roman, and then simply cross-match the two. So that doesn't really work because at these depths and at these resolutions, a lot of your sources are, one, going to be blended. Two, there's going to be red sources that are not detected in LSST, or blue sources that are not detected in Roman. So the one-stop shop to sort of have at least a self-consistent picture is to fully force photometer from one survey to another. So in comes TheFARRM. So this is a helpful sort of plumbing work figure that I've made for myself. So at the far left, we start with a mock data set because we don't have real data yet. So we start with a Cosmos 2025-like universe, where we take the Cosmos Web parameters, assume them to be the ground truth, and then simulate that universe through the various, or the two simulation chains for each survey. So for LSST, that'll be LSST IMSIM, and then for Roman, that'll be Roman ISIM. And then for both tracks, we really try to stay with the native default pipelines for each survey. And we'll talk about that philosophy later as well. So for LSST, that'll be the DM pipelines. So deblend, detect, deblend, measure. And then for Roman, it'll be basically Roman cal all the way from L1 to L4 catalogs. And the way that the TheFARRM comes in here is it takes the L4 catalog output and wedges it back into the source detection step at LSST. So it takes the union of Roman sources and Rubin sources, and then forces basically the deblender to find sources at those locations. So if it was missed by Rubin because of either the source was too red or it was blended, now it's forced to partition your flux according to that. So by construct, the TheFARRM is complete in Roman. For every Roman detection, you will have a Rubin color. It is also, by construct, complete in Rubin as well, because we're allowing Rubin to resolve around its detections as well. So in practice, visually, this is what it looks like. On the far left is our usual WFI field of view. And then because we're simulating HLWS, I'm simulating two passes. So one pass and another at 167 degrees offset. 3 dithers, dithered by your normal line gap 3. And then on the right panel is a bunch of Rubin visits. I've only shown 10 here, but we do up to 30. It's kind of like between year and year 5 depth you would expect. And the resulting images already kind of tell you why we need something better than a cross-match. So this is an example of a very well-separated galaxy in Roman that kind of shows up as one monotonically decreasing blob in Rubin. So how does the TheFARRM do? Sorry, those were backup slides that somehow ended up in the main slide. We look at 3 criteria. The farthest left is the recovery fraction. So as a function of true R-band magnitude, what fraction of resources do you actually gain back in terms of galaxies? So the magenta line is what you get for the TheFARRM, and the dashed black line is what Rubin does on its own. So one, yes, we basically recover every Rubin source that was already detected, and then some. And then those sum are, again, galaxies that are either blended or galaxies that were too red and did not meet the RF 26.5 or 27.5 phi sigma cut. And such an example is shown here on the bottom as well, where the farthest left panel is a Roman detection. It's a very nice compact galaxy. But that is basically absent, at least by eye, in the Rubin image. But when you actually force Rubin to take that source, convolve it with the Rubin PSF, and detect an aperture, you do recover a galaxy that has about the same brightness as it should. So that's shown up here in both the scatter and the bias. First look at the scatter plot. Scatter plot meaning how noisy is your photometry recovery. What we see is that both for the magenta and the black lines, they basically agree with each other down to 26th magnitude. So up until that point, we don't do any worse than Rubin alone, which is good. We're not introducing any more noise into our measurements. And then you might be concerned, why is the FARRM doing much worse after 26th magnitude? And that is purely a selection function. Remember that we're detecting new sources that did not exist in Rubin. So the black line only accounts for the sources that were very well detected to begin with. And this becomes abundantly clear in the bias plot, where if you look at the bias of your recovered photometry, after 26th magnitude, Rubin is, of course, losing flux because it's not detecting the outskirts of these sources. So I'm going to highlight 3 quick applications of this pipeline or data set. One is deblending, of course. So let's focus on the visuals on the right for now. So on the top left is an example of 2 Roman galaxies that are well separated. It's better separated than it seems. This is Z-scale. It's very well separated. And on the right side is the Rubin image, again, of the same source, or 2 sources, rather. Again, so the FARRM wedges itself into the deblend stage of Rubin. So now it's forced to split the original blue flux into the 2 orange fluxes, and then we get a 2-flux or 2-point solution. And if you ask how often does it really happen, the answer is quite often for faint galaxies. So on the far left is just for this cosmos-like universe, what is your Rubin blended fraction as a function of R-band magnitude? And as you can see, past maybe 24th magnitude, about like a third to 40% of your sources are going to be blended in Rubin. And this is just Cosmos, but people have done this for HSC data as well and found even slightly more pessimistic results in terms of the blending. So it's more blending, if not it's going to be more blending than this. Blending is not just important for galaxies and cosmology, it's also really important for stars. So there's going to be a lot of examples where you have stellar binaries that don't have resolved companions in your legacy survey image, as this case, or Rubin in the future. But it will be very well separated in the Roman image. So the FARRM will be a very easy way to identify these kinds of stellar companions. The second quick application I wanted to highlight is star-galaxy separation. So this is a question of, when you see a galaxy, do you call it a galaxy, right? And for Roman, the answer is basically yes the whole time. So that's the green line at the top. As a function of R magnitude, your ability to classify a galaxy as a galaxy is 1. But for Rubin, at least based on morphological classification, this ability drops down precipitously past 24th magnitude. And this is only one kind of galaxy failure mode. There's also stars that are going to be inflated as galaxies that contribute to this as well. And you can see why in the image on the right. So both are Rubin images of a galaxy and a star. I challenge you to find which is which. It's impossible. It's only when you actually have Roman data that you can see the left side is clearly more extended than the right side. And the cross marks are supposed to show you the PSF. You might ask, why is that important? Because stars are really cool too. And especially in the field of trying to look for really faint things like dwarf galaxies or stellar populations, it becomes a real challenge. So we inserted a very realistic looking dwarf galaxy into our sample. It's more of a tongue-in-cheek measurement here. But if you place this very ridiculously, obviously not background structure into the LCC 10-year depth, so this actually is a dwarf galaxy with realistic properties except for its spatial outlet, you wouldn't see it at all in the CMD or on the sky, right? Because you're just swamped by the background galaxies that are all presenting as stars. But even with a single pass of HLWS, you'll just filter out all your backgrounds and voila, you'll get the concentric circles. That's a dwarf galaxy. Same principle applies for stellar streams as well. So if you look at the red box here, it's highlighting what we call like a gap feature in a stellar stream that could or could not show the existence of dark matter subhalos. But in the presence of this star galaxy contamination, it's essentially impossible to resolve this in Rubin alone. But again, with the foreground or the background removal with Roman, it becomes very apparent. And all these are at different distances. Third application is the fact that we now have self-consistent catalog of UGRZY and H-band and even J-band data for all your Roman sources. So an obvious example is applying this to photoz's. Here's a figure from our not successful cyclone proposal. This is showing that even with the addition of one H-band, you'll improve your photo-Z outlier rate by factors of 4 to 6 past redshift 1.5. And this is just one example. Of course, having infrared morphologies and SCD can greatly help your improvement in galaxy evolution science as well. That was a lot of information, but I think it's important to talk about the context and the timeline of this project. So first, I want to highlight really great work being done by the HLIS PIT on also force photometering Rubin on Roman sources. Especially Chunhao's paper just came out on the archive like 2 days ago, so I'll recommend you to go and look at that. I only just noticed that their pipeline is called Slim Farmer, so I'm going to change my pipeline to Thick Farmer instead. A lot of farms in this house. But the main difference between these two pipelines are really the science focus and the timelines, right? The HLIS PIT products are optimized for weak lensing. That's why it was built. The TheFARRM products are, probably not suitable for weak lensing science, but it is absolutely suitable for general astrophysics. And that is also the reason why it works off the L4 catalogs that are very promptly available, on like a week time scale. And because we're doing this at KaiPak and the LSSD USDF is co-located here, here meaning in the Bay, it is actually very straightforward to run this analysis on LSSD pixel data. So all these considered, the TheFARRM, you can think of it as like the general astrophysics photometry pipeline that one could use for doing all the astrophysics that is not weak lensing. Of course, it wouldn't be a Jesse Hahn talk if I didn't harp on about the All Sky survey, and I will not. However, I do hope that the data products like the TheFARRM can help inform and change how the community views the role of Roman in ultra-wide surveys, especially in the era of LSST and other wide field surveys. SphereX, UVX. I got to stop here before I start the whole Nancy talk again. So with that, a big thank you to the Roman SOC and the LSST DM pipeline developers, because that is truly 99.9% of the work. We're just connecting the dots here, and happy to take any questions. Thank you.
Okay. Do we have any questions?
My question is about how you decide if it's a blended galaxy.
Yeah.
I mean, I see it could be, you decided that is two overlapping galaxies, and that's fine, that's your definition, but there's no correct definition. Other people would say, no, that's one galaxy that has two bright peaks in it. It kind of depends on what science you want to do. I mean, if you knew that all of that light is like at the same redshift or something, you'd say, maybe I should just measure the whole thing together. You just
I think these are two very different things. So there is a correct answer, right? There's
not a correct answer. But tell me your answer.
Well, the answer is if they're two different galaxies, that's the correct answer.
We don't know. How do you know it's two different galaxies?
Because you have U, G, R, Z, and Y, and then you could tell the redshift, as you said, or you can look at the galaxy morphology. I mean, it kind of goes back to like the whole, is the SMC one galaxy or two? Sure. But I think it's important to distinguish between shredding, which is a real problem, and that's taking one galaxy into two, right, and real actual blended galaxies. So this is telling you, the real answer why we know this is a blended galaxy is because, we simulated it. And what's important to know is that, where are you? Like we expect at minimum, right, even without shredding, these amount of galaxies to be misclassified as one galaxy. And that is actually really bad for your photoz's as well, because when you combine the flux between two different lights, it's not a linear combination of the two. It just becomes anything. So yeah, there are subtleties to this, but there is a right answer. sometimes. Thank you.
Hey Jesse, great talk as usual. I'm really interested in the star-star deblending scenario for galactic bulge reasons, of course. And so I'm curious if you put any sort of priors on the brightness of each stars from the Roman data for the Rubin data to sort of control for like decorrelation noise.
Yeah, absolutely. So this is a case where it was a conscious decision to not implement something fancy with the SCDs to keep it in the spirit of like, let's stick within the DM pipelines. But you can imagine, especially if you know it's a star, stars are parameterized by basically effective temperature and log G, and metallicity. So you could absolutely use the H band, and especially if you have J band as well, for that to combine with the U-Grizzy to get a more sensible separation of the flux. Yes. So I'm just agreeing that that is possible. It's not going to be the default, output from the farm. Sorry, the thick farmer.
Thanks.
Okay, other questions? I know we're at the end of the day. I want to ask you about the star stuff too, but you know what? I will wait. So I will corner you afterwards and maybe ply you with libations. Anyway, all right.
Yes,
I want to thank you very much for a good talk, and please let's thank all of our speakers once more. And here are the announcements.
All right, thank you so much, Jen. That was great. I have one announcement, and then I will let you go just a few minutes early. This is mostly just fun. I was thinking of the spirit of shifting landscapes. I forgot to mention this. I don't know if people know this, that yesterday morning there was actually an earthquake. I did not feel it, but supposedly some people saw the screen shaking a little bit. Yeah, so now all the non-locals can say you felt an earthquake. Even if you didn't, you experienced an earthquake. Okay, that's it. Thank you, everyone. Have a good rest of your day.